Welcome to G Fun Facts Online. Today we are diving into the science of the wine industry, specifically looking at a revolutionary convergence of green chemistry and circular economics, known as the vine-to-vial movement. In the rolling hills of Bordeaux, the sun-drenched valleys of Napa, and the rugged terraces of Marlborough, a quiet crisis is brewing beneath the canopy of the world's most romanticized crop. The global wine industry is celebrated for its craftsmanship and connection to the earth, yet it produces a staggering amount of waste. For every bottle of wine that graces a dinner table, a significant mass of solid residue, including grape skins, seeds, stalks, and stems, is left behind. This organic byproduct, known as pomace or marc, has traditionally been viewed as a nuisance, often destined for landfills, low-value animal feed, or distillation into industrial alcohol. Simultaneously, the very industry that prides itself on terroir is grappling with a synthetic addiction to plastic. From the clips that hold vines to trellises, to the protective nets that ward off birds, and the mulch films that suppress weeds, modern viticulture is draped in petrochemicals. These plastics, designed for durability, often persist in the soil for centuries, breaking down into microplastics that eventually find their way back into the ecosystem and potentially the vine itself. But scientists and entrepreneurs are unlocking the latent potential within the grape itself to solve the plastic problem it unknowingly contributes to. This is a journey into the molecular alchemy that transforms the humblest winery leftovers into advanced, biodegradable plastics. To understand this transformation, we must first analyze the raw material. Grape pomace is not merely compost, it is a complex chemical treasure trove waiting to be mined. The Food and Agriculture Organization estimates that the global wine industry processes over 75 million tons of grapes annually. Approximately 20 to 25% of this weight becomes waste. That amounts to roughly 15 to 20 million tons of solid residue generated every single year. In a world desperate for renewable biomass to replace fossil fuels, this is a goldmine. Unlike crops grown specifically for bioplastics like corn or sugarcane, which compete with food production and require arable land, grape pomace is a true waste product. It requires no additional water, fertilizer, or land to produce. The magic lies in the molecular structure of the grape's leftovers. First, we have cellulose and hemicellulose found in the stalks and skins. These are the structural backbone of the vine, consisting of long chains of sugar molecules that can be extracted and processed into strong, transparent films. Then there is lignin, found in the seeds and stems. Lignin is a complex organic polymer that provides rigidity to the plant. While lignin is notoriously difficult to break down, new technologies are turning it into a valuable filler that adds strength and water resistance to biocomposites. Perhaps the most exciting and underutilized component is cutin. Cutin is a waxy biopolyester found in the cuticle of the grapeskin. It is nature's own water-repellent plastic, designed to keep moisture inside the fruit. Finally, we have polyphenols. While primarily known for their antioxidant properties in wine, polyphenols can act as natural stabilizers in plastics, preventing them from degrading too quickly under UV light, which is a crucial property for agricultural films used outdoors. Turning a pile of wet, sticky grape skins into a rigid plastic bottle or a flexible film is not a single process, but a choice of several sophisticated chemical pathways. Let's look at the first major method, known as Pathway A, or bacterial fermentation. This is the route to producing polyhydroxyalkanoates, or PHAs. These are polyesters synthesized by microorganisms as a form of energy storage. The process begins with the sugar-rich lees and liquid residue left after pressing. While winemakers want to ferment these sugars into alcohol, bioplastic scientists want to feed them to specific bacteria, such as Bacillus or Cupria vitis nectator. The science here is fascinating. Under stress conditions, such as limiting nutrients like nitrogen, these bacteria gorge themselves on the grape sugars. Instead of growing larger, they convert the carbon into intracellular granules of plastic, essentially fat reserves made of polymer. These granules can grow to occupy up to 90% of the bacterial cell's dry weight. The bacteria are then harvested and broken down, releasing the plastic granules, which are washed, dried, and processed into a powder that can be melted and molded just like conventional polypropylene. The result is a fully biodegradable plastic that is biocompatible and has thermal properties similar to synthetic plastics. Another method is lignocellulosic extraction. Research teams have pioneered methods to extract cellulosic fibers directly from grapevine canes, which are the pruned branches. The canes are dried, ground, and treated with an alkaline solution to strip away the lignin and hemicellulose, leaving behind pure cellulose fibers. These fibers are then dissolved in eco-friendly solvents to create a viscous dope. This dope is cast onto plates or extruded through rollers. As the solvent evaporates, the cellulose chains rebond, forming a clear, flexible film. These films have shown exceptional tensile strength, often higher than standard petroleum-based plastic bags. More importantly, they decompose in soil within 17 to 60 days, depending on moisture levels, leaving behind nothing but organic matter. A third pathway utilizes the cutin from grape skins to create hydrophobic coatings. Synthetic plastics are prized for their ability to hold water without dissolving. Nature's answer to this is cutin. Researchers are developing methods to extract fatty acids from the pomace using green solvents. Once isolated, these fatty acids can be polymerized to create a water-repelling coating. This is particularly valuable for lining paper cups or cardboard wine boxes, replacing the thin layer of polyethylene that currently makes such packaging difficult to recycle. This innovation mimics the natural barrier of the fruit itself, effectively using the grape's own skin to protect the product made from its juice. The transition from lab bench to vineyard trench is being led by a diverse group of global innovators. In Italy, a company called Vegea has paved the way for grape-based biomaterials. Based in Milan, Vegea takes grape marc and polymerizes the vegetable oils and fibers found within it to create a leather-like material. They have collaborated with major fashion houses and automotive brands like Bentley to replace animal leather and synthetic vinyls. Their proprietary process demonstrates that grape waste can yield durable, high-performance materials that are aesthetically pleasing, proving to the market that waste can be luxury. In France, the startup Planet of the Grapes has developed a material called Scion. They utilize a slow-drying process to preserve the natural tannins and colors of the grape waste, resulting in a creamy, marble-like material. Unlike flexible leather alternatives, Scion is often used for harder applications, such as veneers for furniture or luxury packaging. Their work highlights the aesthetic versatility of the material. It does not just look like plastic, it looks like a new class of organic stone. In the Southern Hemisphere, the Crown Research Institute Scion in New Zealand has focused on a pragmatic, high-impact application: vine clips. New Zealand vineyards use millions of plastic clips annually to hold nets. These clips often fall to the ground and are tilled into the soil, creating a microplastic nightmare. Scion developed a composite material using grape pomace mixed with PLA, or polylactic acid. The grape pomace acts as a filler, reducing the cost of the raw bioplastic and accelerating the biodegradation process. A winery can essentially prune its vines, send the waste to a processor, and buy back clips made from their own grapes to use in the next season. If a clip falls, it simply composts back into the soil it came from. In Chile, a massive wine exporter facing significant waste management challenges, ZEAplast is working on valorizing grape pomace for thermoplastic applications. Their research targets the active packaging market. By incorporating grape extracts rich in antioxidants into the plastic matrix, they are creating films that not only hold food, but actively extend its shelf life by scavenging oxygen and preventing oxidation. The true value of grape-based bioplastics is revealed through life cycle assessment. Conventional plastics are carbon positive. They extract sequestered carbon from the earth and release it into the atmosphere. Grape-based plastics are part of the current carbon cycle. The vines absorb CO2 during the growing season. When the waste is converted to plastic, that carbon remains locked in the material. Even when it eventually degrades, it only releases the carbon that the plant absorbed months prior, resulting in a net neutral or even carbon negative footprint if the processing energy is renewable. Soil health is another critical factor. One of the most insidious threats to agriculture is the accumulation of sterile plastic residues in topsoil. Polyethylene mulch films, widely used to suppress weeds, often tear and remain in the field. Over decades, this reduces soil permeability and microbial diversity. Grape cane mulch films are designed to rot. As they break down, they add organic matter back to the soil, potentially feeding the soil microbiome rather than choking it. The degradation products are non-toxic, unlike the phthalates and bisphenols, often leaching from traditional plastics. Diverting this biomass into plastic production also turns a disposal cost into a revenue stream and mitigates local pollution risks, such as acidic leaching into groundwater or methane production from anaerobic rotting. The versatility of grape-based biopolymers allows for a wide range of applications. In the vineyard, we see vine clips and ties that degrade after one season, as well as mulch films colored black with the grape's natural anthocyanins. There are also controlled-release fertilizer coatings, using hydrophobic cutin-based polymers to coat fertilizer pellets, ensuring nutrients are released slowly to the vine and reducing runoff. In the winery, composites are being tested for secondary packaging like crates and gift cases. The foil capsule covering the cork, typically made of aluminum or plastic, is a perfect candidate for biopolymer substitution. Even labels can be made from paper derived from stalk cellulose and coated with cutin for water resistance. Beyond the industry, there are consumer goods applications. The luxury skincare market is hungry for sustainable packaging. A cream made from grapeseed oil, packaged in a jar made from grape skins, offers a compelling marketing story. The automotive industry is also a prime target for durable, leather-like biomaterials for seats and dashboards. However, if the science is so sound, why aren't all our wine bottles made of grapes yet? The answer lies in the brutal economics of commodity plastics. Petroleum-based plastics are artificially cheap, subsidized by a massive, century-old fossil fuel infrastructure. Bioplastics currently cost anywhere from 2 to 5 times more to produce. While consumers claim to want sustainability, their willingness to pay extra is limited. However, in the luxury wine market, where a bottle might sell for $50 or $500, an extra few cents for vine-sourced packaging is easily absorbed and even serves as a value-add differentiator. Seasonality and logistics also pose challenges. Grapes are harvested once a year, creating a logistical spike. A bioplastic factory needs a steady supply of feedstock year-round and cannot operate only during the harvest months. Preservation techniques like drying and ensiling are required to stabilize the pomace so it can be stored and processed throughout the year, which adds energy and cost to the life cycle. Heterogeneity is another hurdle. Not all grapes are the same. A Cabernet Sauvignon skin is thicker and has a different chemical profile than a Pinot Grigio skin. Standardizing the feedstock to ensure consistent plastic quality is a major engineering hurdle. Furthermore, approving new materials for food contact is a rigorous legislative process. Proving that no unknown allergens or compounds migrate from the grape plastic into the food is essential. Looking to the future, the next decade will likely see the industrial symbiosis of the wine and chemical industries. We are moving toward a future where the concept of waste is obsolete. Imagine an integrated biorefinery adjacent to a major wine cooperative. Fresh pomace arrives and undergoes polyphenol and tartaric acid extraction for pharmaceuticals. The remaining biomass is fermented to produce PHA bioplastics. The solid fibrous residue is then processed into packaging board. The output is high-value chemicals, plastic pellets, and packaging material with zero waste. Future grape plastics will also likely be active packaging. Research suggests that the residual antioxidants in the plastic could actively protect the wine from spoilage, potentially reducing the need for sulfites. A bottle that keeps the wine fresher because it is made from the grape itself is the ultimate synergy. The journey from vine to vial is more than just a technological feat. It is a philosophical realignment. For decades, we have treated the fruit of the vine as two separate entities, the juice, which we revere, and the body, which we discard. By turning that body into the vessel that holds the juice, we close a circle that has been broken for too long. In this new era of material science, the bottle is no longer the vessel of waste, but the vessel of a sustainable future. Thanks for listening to Fun Facts Online.